The next topic is malleability. The ability of a metal to be hammered or rolled into thin sheets without cracking. Ductility means into thin wires. Malleability means thin sheets. High malleability lets make sheet, plate and foil and performs operations like rolling, stamping and deep drawing without tears. This is important, without tears. So this is best example is aluminium. Aluminium is highly malleable because aluminium foil is produced by repeated rolling. It prevents cracking as thickness drops. And other examples are gold, silver, copper. These are also other examples because it's also easy to form into a thin sheets or foils. And high temperature and fine clean microstructures generally increase the malleability. This is the malleability. The next topic is weldability. Weldability is how readily a metal can be welded without cracking, excessive distortion or losing its desired mechanical properties. It depends on chemical composition, thermal conductivity, microstructure and the need of preheat and post-weld heat treatment. Good weldability means you can make sound joints reliably and economically while keeping the parts required strength and toughness and hardness in both the weld metal and heat affected zone. In both weld metal and heat affected zone. Next, we deeply saw a chemical composition. Example is carbon and alloying. What is chemical composition? Higher carbon or carbon equivalent, higher hardenability and risk of heat affected zone cracking. What is the action required for chemical composition? Means use preheat and low hydrogen consumables and controlled heat input. It considers post-weld heat treatment or temper for hard structures. The next one is thermal conductivity. The metals like aluminium or copper pull heat away fast. So the risk of lack of fusion and distortion control the issues. We increase heat input or travel speed appropriately or use proper joint preparation and maintain interpass temperature. This is the action we take. The next one is microstructure. Martensite prone or coarse microstructures rise cracking risk. It increases the cracking risk and it reduces the toughness. So we prevent that, preheat to slow cooling and choose suitable filler and consider PWHT to restore the toughness. The next one is preheat and post-weld heat treatment. Preheat lowers the cooling rate and helps drive out hydrogen. It reducing cold cracking. So preheat reducing the cold cracking. Next one is post-weld heat treatment. It tempers the heat effect zone weld and it reduces the residual stress. It reduces the residual stress and can recover the toughness. Here post-weld heat treatment recover the toughness. The best example is in low carbon steel has excellent weldability, often no preheat or only a minimal preheat, and high carbon steel prone to cracking unless treated properly. So preheat plus controlled heat input plus low heat consumable and post well heat treatment or temper is specified. So in high carbon steel these are specified. In low carbon steel excellent weldability and this has no preheat or minimal. This is a weldability. The next one is elasticity. Elasticity means springs back in a simple word. It's a material's ability to return to original shape once the load is removed. Within the elastic range, stress is proportional to strain. This is the Hooke's law. If we put a little load, it stretches a little and springs back and go past the elastic limit, it won't full return. That becomes plastic deformation. And the formula to mention the Hooke's law is, this is stress, this is strain, E is Young's modulus means stiffness. This is E means stiffness. Higher E, stiffer, less elastic stretch for the same load. So formula is sigma is equal to K. This is the formula for Hooke's law. It predicts deflection or spring back in parts like beam, shaft, springs. These are the examples. Example, spring steel in suspension systems. Spring steel is vehicle suspension, stores energy elastically and returns. We all see the bike. So they are using a springs for giving a ride comfort and control. The next topic is plasticity. It's the ability of metal to permanently deform without breaking once the stress goes beyond the elastic limit. That means past yield. The shape change remains after unloading. So this is the plasticity. Plasticity is what allows us to form parts safely, means bending, drawing, rolling and extruding and forging. All rely on controlled plastic flows instead of fracture. Below the elastic limit, the metal springs back. Beyond it, atoms slide to new position and the metal keeps the new shape. That is plasticity. What is the behaviors in the plastic regions? 3 behaviors. Yield point. Yield point is start of permanent deformation. Next one is strain hardening. Strain hardening is metal gets stronger and harder as it is deformed. The next one is necking. Necking, that means fracture at very high plastic strain in tension. This is the key behaviors in the plastic region. And what are the keys affects plasticity? That is temperature and strain rate and microstructure and prior cold work. These all affects by plasticity.